just find our PowerPoint. Did we all watch those videos from Canvas? Does anybody have any questions from those? Any thoughts? Does anybody want to comment on that weird guy and his who's way too enthusiastic about lights? That's what I want to hear. That proves that at least somebody watched those videos. I just think that dude is hilarious. He gets super excited about his little his lights. Anyway, okay. That's my PowerPoint button. All right, can everyone see the slideshow there? Cool. No, we'll get straight into it. So the next one we're going to look at is the low pressure sodium vapor lamp, as you can see there. So we talked about the high pressure sodium lamp yesterday, and this is essentially the same thing. It's just operating at a lower pressure. Just note that a few things occurred to me as I watched those videos myself. When we're talking about each of these types of lights, we've had mercury vapor, sodium vapor. In this case, we're talking about metals that are inside the arc envelope. So, although we call them a gas discharge light, and then we say mercury vapor, sodium vapor, something like that, that kind of gives an impression that that the gas inside those lamps that is doing the work is mercury or sodium or something like that, and it's not true. The gases in there, I think, are just standard inert gases, argon or something like that. But it's actually metal inside there that gives the different types of lights their different characteristics. And so what's happening there is that we have actual solid pieces of those metals inside the arc tube, and then as the lamp warms up and when that arc is struck, those metals melt and eventually vaporize. So obviously it's running at a very high heat, and then that's what's, as I said, just giving that's what's giving the characteristics of the particular lights. So it's not mercury gas, it's not sodium gas, it's actually physical sodium or mercury metal inside there. And that's part of why they take a bit of time to warm up and have heating elements and all of that other stuff that's going on there. And that's in order to, it takes a little bit of time to vaporize those metals inside a cold tube. So we'll get that warm-up period where they're perhaps not running at full brightness. And you'll also notice with many of these that the color will actually change as it warms up. Anyway, it's a low-pressure sodium vapor lamp. So we're talking about a lamp here with, again, an envelope in there with gas in it. And it has actual sodium metal in there. If you watch the video for this one, you'll know this, but if you didn't, bear with sodium is highly reactive. You can find videos on YouTube of people like chucking big chunks of sodium metal into water and creates big explosions and stuff like that. So sodium is highly reactive with both oxygen and water. So some care needs to be taken with these types of bulbs, sodium vapor bulbs. If you smash them, then the actual sodium inside there can react with the air, cause fires and that kind of stuff. So we have here a very simplified, typical wiring diagram or circuit for a low pressure sodium vapor lamp, and you can just see here we just have basically a ballast and nothing else. So power coming in, ballast, it's giving us our high voltage, and the lamp itself. So inside that low pressure sodium vapor lamp, the discharge tube is either linear with contacts at the end or bent into a U shape, in which case dimples in the U tube act as sodium reservoirs. Again, remember we've got that solid sodium in there when the bulb is cold, so it's little reservoirs inside there to hold that. Common ratings are 35 up to 200 watts, and it has a better efficacy than the high pressure sodium lamp. Disadvantage of the sodium vapor lamp is it emits an almost monochromatic light, which means objects it illuminates appear as grey, black, or shades of yellow. So a couple of things here. It does have a better efficacy than the high pressure sodium lamp, and in fact the low pressure sodium, I believe, is the highest light output per watt of any of the lights that we look at, including LED. So I think it's the only thing that was superior to an LED in terms of the light output for each watt. Downside of the sodium vapor, and it's a massive downside, is that the color rendering, the spectrum that it emits, and therefore the color rendering is as bad as it can get. And I've talked about this before. So our low pressure sodium lights are these are the yellow street lights that you'll see. You'll still see them from time to time. So the light that the lamp emits is yellow, and the way things look under it, it doesn't render any colors in particular very well. So this is where you'll struggle to be able to tell the difference between green and red, for example. Under that yellow light, they all look the same. So it's a very, very poor quality light, but a very high output. Hence, it's used in areas where we want a lot of light, but we're not concerned about the quality. So street lights are typical usages. If you watch their video, they also talk about lighting in tunnels and stuff like that. It's a low fatigue type light, I guess. So it doesn't cause strain on the eyes. So in tunnels and stuff like that, it's less likely to distract or annoy drivers. And in that situation, the color rendering is not particularly a problem. As with any gas column, the control equipment for a low pressure sodium vapor lamp must limit the circuit current. A transformer is used which has a high leakage reactance. The initial discharge is established through a neon or xenon filling in the tube. This, as I said before, we will have some sort of inert gas in there. I mentioned argon, but in this case we've got neon or xenon. The sodium in the tube is solid at room temperature. In older type tubes, a starting strip is connected to one electrode. Later models do not require this. So the ballast that we use to get a high voltage to strike the arc, once the arc is struck, doubles as a choke or as a resistance in order to limit the current through the tube. It's because, as I mentioned yesterday, once we've struck that arc inside the tube, there's very little resistance, and therefore it will just operate as a short circuit. We'll blow the circuit breakers unless we have something in the circuit that's going to provide some resistance to limit the current. And here's our color spectrum or output spectrum of the low pressure sodium vapor. If you go back and compare this to any of the other ones, or if you remember what they look like, you'll see that this is easily the worst color output that we'll see from any of the lamps that we look at, any of the ones that we've looked at so far, and any of the ones that are still coming. So there's no output on this in the red and orange spectrums, and nothing from green through blue, purple into the white end of the spectrum up here. We're just getting one little spike at the yellow spectrum. So terrible quality of light, massive light output, terrible quality of light. So summary for that one, we're going to get about 16,000 hours out of that. So that's reasonably, that's a pretty long time. I think one of the ones we looked at yesterday, we might get up to about 20,000, but this is right up there, 16,000. Remember, if we're looking at 2 to 3 hours a day, then 16,000 hours is equivalent to pretty close to 16 years. So 2 to 3 hours a day would be about 1,000 hours per year in a workshop or warehousing scenario where we might have these lamps on all day. Then we'd be looking at something more like 3,000, 4,000 hours a year. So even in those cases, running all day, every day, we're still going to get 4 or 5 years out of one of these. The street lighting might run a bit longer, 12 hours a day maybe, in the if the street lights just come on all night. So you're still going to get a few years out of one of these lights, which is a huge advantage. If you think about street lights, the factors that are important for street lighting are quite different to what we would see for most other lighting scenarios, right? And the street lighting, we don't particularly care about quality of light. It's not really important. Nobody is using street lights to do any kind of any work or anything like that. Street lighting needs to be powerful or at least efficient, right? So we want as much or as high light output as possible in street lighting, because not because we need a huge amount of light necessarily, but we just don't want to pay a lot for it. So the most light that we can possibly get for the minimum power input is the best. I mean, just think about how many street lights there must be in Auckland. The lighting bill must be excuse me, the lighting bill for street lighting must be obscene. Even a 10 to 20% efficiency gain across that network would be massive. Excuse me. Goodness. So yeah, really important to have high efficiency lights, as in high output for low input costs in street lighting or any sort of massive outdoor type of lighting. The third thing would be maintenance costs, and maintenance cost constitutes not only the replacement of the bulb, the physical bulb itself, as in how often do I have to replace it, as we just talked about here. We might get 4 or 5 years out of these ones in a typical street lighting situation. But if you think about the cost to actually do that, so replacing a lamp in a street light is not a 5-minute job, right? You're going to need access, so we're going to need some sort of cherry picker or something like that to get up to the light, which means we probably need a dedicated vehicle. You probably need 2 people. So to change all the lamps in any given street might take 2 people a whole day. If you think about how many there would be, again, thinking about Auckland, uh, you could easily surmise that it's possible that you'd have 3 or 4 street lighting crews if you're using lamps of this kind of type. You might have 3 or 4 street lighting crews who just drive around all day, every day, and replace lights. And by the time they finish, they just go back to the start and start again. With the number of streets, the pure number of lights that must be in that network, it would be a continuous job for people to do that. So having efficient lights is really important. But if you think about it, having lights that last a long time is going to be really important as well. Again, if we could get lights that last even 10 or 20% longer, then that dramatically reduces those maintenance costs, because we just don't have to do as much work to replace them. So that's where LEDs are probably still, even though it's the one type of lighting that's likely to be more efficient in terms of light output than LEDs, the additional lifetime of an LED is probably going to still make it more cost effective, even if it was slightly more expensive to run, if you only had to replace them half as often, because you could get 30 or 40,000 hours out of them. That's probably going to make the difference in terms of overall cost. So thinking about that, I guess it's important to note that the different what you call it, applications, then even if we're just talking about cost, then different factors might play a greater or lesser part in whether that cost is the deciding factor, right? So you've obviously got the initial setup cost, the cost to buy the fitting itself and install it. Then you've got the running costs, as in how much power does it take to run it, and how much does that cost me, and then ongoing maintenance costs. How often do I have to replace these things? What does it cost? What does it cost to replace them? See your question there, Jade. Are those costs covered in rates? Yes, they are. So that's part of the council's operating costs, is not only obviously running street lights, but then presumably undertaking all of the maintenance for them as well. Massive job, right? Massive job. Think about it. These are little things that underpin our society that we don't even think about. I mean, just think about traffic lights, right? That's probably an even bigger deal. Street lighting, if you have a blown street light, you could probably leave that out for a few weeks, and I'm certain that you guys would have seen that before, that maybe the street light outside your house blows, and it might be out for a few weeks or a couple of months before someone comes to replace it, and it's not the end of the world, right? They'll get around to it eventually. But if you think about a traffic light, and again, traffic lights are going to LEDs nowadays, so they're becoming more reliable. But in the past, I mean, going back 20 years ago, maybe a bit more, that's not even that long ago, you would have traffic lights just be ordinary incandescent bulbs. You just got a big fitting with the different color plastic covers, but behind there it's just an ordinary incandescent bulb, which, as we said, is probably getting 1,000 to 2,000 hours. So you can imagine the work that must go on behind the scenes to maintain those things, to make sure that they're working. Because if they don't, you can't just leave it for a couple of months. Like, people will drive into each other and stuff if traffic lights aren't working. And if you start delving into some aspects of maintenance theory, you'll find that in general, it's not cost effective to wait for equipment, particularly equipment that has what we would call consumable parts, right? So like a light bulb is a consumable part. It has a defined lifetime, and it's going to break down and need to be replaced. So any equipment or machinery that has consumable parts in it, it's generally not cost effective to wait for it to break down and replace it. Because that means if you have an intersection that, say, has I don't know, a typical intersection might have 8 or 10 individual traffic light fittings, and then each of those would have 3 bulbs in it. So, or more if you got turn arrows and stuff like that. So might be 30 to 50 individual lamps in a typical intersection. So if you replacing lamps as they break, that means, again, in terms of labor costs, you've got somebody going there every time something breaks down, and you just don't want to do that. The time and cost of that is massive compared to just turning up to an intersection and replacing all the bulbs at once on a schedule, that regardless of whether they're working or not working. So they start thinking about this stuff, as I say, realize that there's a whole bunch of stuff that we just don't see. It's these invisible infrastructure things that underpin our society. If this stuff didn't work or didn't happen, would just fall apart so rapidly. Maybe not fall apart, but just the easy kind of lifestyle where we don't have to think about this sort of shit would disappear so fast. Now, yeah, you're right, Jay. You just don't think about this kind of stuff. But if we're, to bring it back to lighting, rather than me just rambling about random infrastructure stuff, when you do start thinking about that, you realize that, things like lifetime of the bulb and how much it costs to replace it, what do they cost to power them? There's probably somebody sitting around with it who has the job of literally just sitting there calculating this stuff all day, every day. I could almost guarantee that there was somebody at the Auckland Council, and probably every council, who over the years is tracking the cost and efficiency and life expectancy of LED lamps, and then they probably one day was the day that the cost came down to a point, or the life cycle went up to a point where somebody's going, okay, it's now cost effective to do this. And on that day, they would stop installing whatever other light, and now we're only going to put in these LEDs, because I guarantee you there's people out there who know this stuff intimately, that they've got those equations that they're probably running every day to work out that total life cycle cost of different types of lighting, so on and so on. Anyway, so pros of our low pressure sodium, they're one of the most efficient bulbs, so we get the greatest light output per watt, and they have a long lifespan. They have the worst color rendering of all the bulbs. It's that monochromatic yellow. I think we might have one of these. I know we had one at Otara campus, and I'm pretty sure I chucked it into a box somewhere to bring it down to the new building. We'll have a look next time we're in the workshop, and I'll see if I can set it up for you. But if you put that in a dark room and you fire it up, you can really see what that color rendering looks like. And it's quite an eye opener when you see it and realize why I continually grab on about color rendering, I guess. Another con is that the initial setup is costly. They're fairly expensive bulbs, or fairly expensive lighting system. Of course, that can be counteracted by the low running costs, depending on the application. Again, you would be doing those calculations depending on your particular setup. Efficiency 90 to 180 lumens per watt, and remember, again, as a benchmark, we saw that incandescents something like 10 to 15 lumens per watt, so way more efficient than an incandescent. And then our LEDs were something like 100 lumens per watt. So even at the lower end of efficiency, they're competitive with LEDs, and at the higher end of the efficiency, they run in excess of LEDs. But as I feel like I say all the time, if LEDs aren't more efficient than the low pressure sodiums, it won't be long till they are. The technological advances in LED lighting technology are so fast. I've been following LED lamps for this exact reason, calculating lifespans and total cost of ownership for a number of years, and it continually shocks me how fast they're changing, how much better they get year on year. I made it my mission. So the reason I got this kind of little fetish for LED lights is when I was branch manager in the fuel industry, I realized that this is an area that we could target with our customers. So particularly the under canopy lights at gas stations, typically maybe not low pressure sodium, but certainly gas discharge lights, usually metal halide, which we haven't come across yet, but also mercury vapor. And you know, for my guys to go and replace one of those bulbs, it was going to cost a service station owner something like $700 to $800. It's a couple of $100 for the bulb. You're going to pay $100 to $150 on top of that for hiring a scissor lift. You're going to need 2 people because when we're working at heights, we always need a spotter. And the job itself only take about an hour. But by the time you get 2 people there, you're talking about another couple of $100 in labour costs. So yeah, $700-800 to replace one bulb is not unheard of. And so I sat down one day and did all these calculations to work out how much I would charge somebody to install, take out their gas discharge lamps, the price of new LED fittings, working out the comparison of power costs, how much it's going to cost you to run, and the big cost saving was always in maintenance costs. They're going to have a high initial outlay to actually get rid of all of their existing lights and put new ones in. It was going to cost, you know, for a typical gas station, it would be something like $8,000 to $12,000. They'll have a reduced power cost, although when we say reduced power cost, they're about half their power cost, which is going to take the cost to run their lights maybe from $200 a month to $100 a month, which is not massive. I mean, it is over time, but when you're talking about $12,000 to replace all your lamps, then saving $100 a month doesn't look particularly appealing. But what I always tried to convince people is that if it costs you $700 or $800 every time I have to turn up and replace one of those lamps, you know, that ongoing maintenance cost increases so fast. If you put fresh LED fittings in there, no one will be back here to touch them again for 20 years. So your maintenance costs essentially drop to zero. So I spent a lot of time on that project. I only ever managed to convince one person to do it, which was a bit of a shame. I spent about 6 months on that. But again, that's like going back perhaps 6 or 7 years. So the gains that you'll get out of retrofitting LEDs and taking out your gas discharge lamps are increasing all of the time. And in fact, if you go around and look at any service station that has been built in the last 5, 6, 7 years, you'll notice that 100% of the under canopy lights there are LEDs now. They don't use the gas discharge lights, which proves my point, and also gives me that validation that I was ahead of that curve. So I was trying to push this on people before the oil companies had started using it. But 100% they're doing that now. And actually, now that I think about it, if you're thinking about this gas discharge stuff and wondering where it would be used, like we've talked about warehouses and workshops and stuff like that, but the most common place you're likely to see gas discharge lighting is under service station canopy. So next time you're at a service station at night, have a look. That's where you're going to see these different kind of lights. Anyway, so that's our low pressure sodium. Any questions on that? Or any questions on any of the long rambling blah 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 that I've just rattled off? No, everyone's happy. Is everyone still there? Just like raise your hand, push the raise hand button, and I know you're alive. Good. I've got at least 2 people. Oh, 3. Well done. Just look, who have I got here? Who are we missing? A few no-shows today, eh? Shame. That's a real shame, team. I guess I don't have to tell you because you guys are the ones who are here, but I would think it's a shitload easier just to jump on your computer and watch me talk for a couple of hours than actually have to get up and put clothes on and come to class and all that sort of stuff. So I don't quite understand why people skip these classes, but there you go. Anyway, all right, so that's our low pressure sodium. So we'll move on to metal halide. So metal halide are probably the gas discharge lamps you're most likely to see in kind of general purpose scenarios there. It tend to be a bit better in terms of light output and color spectrum than most of the other ones. So the mercury halide or metal halide lamp has a similar construction to the mercury vapor lamp. Metal halide has a much shorter discharge tube. It's not a mercury lamp, but a series of lamps combined within a single discharge tube with output characteristics of different mixtures of elements. Such metals as dysprosium, thallium, indium, or sodium are introduced into the mercury discharge tube. The mercury spectrum is suppressed, reducing ultraviolet radiation. Adding metal atoms partly compensate by emitting a wider range of spectral light bands. The light distribution is either a white or mainly colored light, depending on the relative proportions of metal used. Yeah, so at the start of this session this morning, I talked about that when we're talking about these metals, mercury, sodium, so forth, in our discharge lighting, it's physical metals that are inside the gas that vaporize when it heats up, and that they give each of those different lamps their particular characteristics. And obviously metal halide is no different. So the main difference here is that we're using, rather than a single metal, we're using a variety of different metals. To give different characteristics, so like counteract each other or complement each other, and they give different characteristics. And in this case, in the metal halide, we're getting different light spectrums produced because of the different metals in there. And that's obviously, as we've seen going through the different types of gas discharge lighting, that one of the main disadvantages is the limitation of light spectrums. So at its core, a metal halide lamp is a mercury vapor lamp. It's the same thing. But it has different metals added into it to tone down that yellow, green, blue, I think, that we get out of the mercury vapor, and then to bring up the color spectrum in other areas. So we get a much more even spread across the light spectrum from a metal halide than we would from a mercury vapor. And I mentioned yesterday that whilst different types of gas discharge lighting might appear on the surface to be the same, obviously we know that they're different and the control gear is different, so you can't swap one to the other. Now, don't quote me on this because I might be wrong, but I have a vague recollection that a metal halide and a mercury vapor are interchangeable. I think the control gear is similar enough that you can actually swap them out. And the fact that we're saying here that essentially a metal halide is a mercury vapor lamp just with some different metals in it would tend to support that hypothesis. But as I say, I can't remember that off the top. I can't remember that whether that is exactly true or not, so don't quote me. All right, so we have our pretty diagram of our lamp here. Very much along the same lines as all of our previous ones. We have our discharge tube here, or arc tube, the outer glass envelope, so on and so forth, electrodes. And here's our here's our light spectrum for the metal halide. So it's still not that nice smooth gradient that we see with the incandescent. We're not getting light at every single part of the spectrum, but you can see we've got enough across the different areas: red, orange, yellow. Still got quite a high spike on the yellow. That's due to the mercury vapor. Green, blue, and into the purple as well. That means that, at least to our eyes, this will appear to be quite a natural white light. Well, it won't appear to be a natural white light. It'll seem quite artificial, but it's way more natural than any of the other gas discharge ones we looked at, because it has a lot greater output across the spectrum. This makes it an ideal lamp for growing stuff. This is the one. This is the one team. Look, we're going to give it all of the spectrums that the plants need. Metal halide. Although I think in some large growing operations they actually supplement metal halides with low pressure sodium. There's something about that yellow light from the low pressure sodium, I think, that doesn't give plants everything that they need, but there's I think they might need more of that than other spectrums. But I don't know. How would I know? I don't know anything about this stuff. Do I know? No, I'm just making it up, mate. I don't know anything. I'm just trying to sound cool to the kids, you see. Just want to show that I'm hip so that you guys will like me. Okay. Metal halide lamps. Using metals in their elemental form would attack the discharge tube, therefore halides of the metal are used, the most common being the iodide, for example, sodium iodide. These lamps need a higher starting voltage. The voltage is provided by an electronic igniter, which generates a very short duration, high voltage pulse and is connected across the lamp terminals. Yeah, so it's just saying there that if we used all the metals that we want inside that tube, if we use them in their pure form, it's going to cause us problems. They'll react with the glass of the tube. So we use halides. Look, I'm not sure what that word halide means in this context. But from that description, it's telling us that we're using some sort of compound. So it's not the pure metal. Yeah, we need that high starting voltage. So again, we're going to have complicated and probably expensive control gear in order to ignite these type of lamps. Advantages: the lamp has a high efficacy, so we're getting a lot of light output per watt, and good color rendering properties, as we saw in that spectrum graph. A better light across the spectrum, and therefore that's going to appear to be a better quality of light to our eyes. Here's our circuit diagram here. We have a ballast there, which helps to provide us our high voltage spike, and also acts as a choke, remember, to give us some resistance once we've struck the arc. And then we have the this big silver cylinder here, which is our igniter. So that's it's probably some sort of capacitor, to be honest. So that'll be charging up slowly off the ballast, and then providing a high energy spike into the lamp to ignite it. The summary on metal halide: lifespan 6,000 to 10,000 hours, so less than the two different types of sodium vapor, but still a reasonable amount of time. They're very efficient. They give a brilliant light, so a very white light. They come at different color temperatures, so we can get something that's more cool white or daylight, or something that's a bit warmer, so slightly lower on the color temperature scale if we need it, and they have good color rendering. The cons, that the cost of both the fixture and the bulb, and they burn quite hot. Um, if you watch the video on the metal halides, the guy talked in the video about mounting them in different positions, and that if you mount them horizontally, they tend to last a little bit less because the arc will be closer to the arc tube and therefore will burn it out faster. From memory, with the metal halides in particular, and possibly the mercury vapors as well, when you buy them, you can actually buy variants on them that are designed to be mounted horizontally or vertically. So they're at the end of the part number, it'll have a V or an H. Again, it's quite important to get the correct one. We obviously don't want to mount a bulb that is designed to operate vertically in a horizontal position. We're going to get about 60 to 125 lumens per watt, so it's competitive with LED in terms of efficiency. Uses, places where there's a lot of light needed, such as outdoor areas and retail shops, frequently used as sports arenas, stadiums, auditoriums, and convention halls. Yeah, so stadium lighting is a common usage of stadium lighting is a common usage of metal halide lamps. So if you think about Eden Park or something like that, those big lighting towers with heaps and heaps of bulbs on them, they're really bright and really white. They're mostly metal halides. And actually, if you've ever been at one of those grounds, when they fire those lights up, you can see that start-up time, right? So you'll see them turn on, and you can see that the lights are going, but there's not really any output. You're not seeing any light from it. And then over 5 or 10 minutes, they slowly brighten. It's a good example of that that time it takes discharge lamps to brighten up. And the reason that we use them in sports stadiums is because we want color rendering. You'll still notice in those contexts that the colors don't appear to be 100% natural, but you're going to get a much better color rendering, which is obviously going to be important for the people on the pitch playing, whatever that game might be. If you're thinking about cricket, if you've got a cricket ball coming at you at 150 kilometers an hour, you're definitely going to want to be able to identify that against the background. So color rendering is important, but also in a television context as well, right? So we don't want to be paying to watch a game at home and to have that really poor quality light, that like if you couldn't differentiate between the different jersey colors and stuff like that. So color rendering quite important for stadium lighting, and hence metal halide is often employed there. Notes not to be used near flammable materials, because these are the hottest types of gas discharge lamps, and the bulbs must burn in a certain position. So that's what I mentioned before, that they should either be horizontal or vertical, and you want to buy the correct lamp for the correct mounting position. Okay, fluorescent lighting. Look, I don't know if you guys can hear how shitty my voice is, but I feel like ass. So I think we'll take a 5 or 10 minute break. I'll try and do short breaks frequently during the day, just so I can get some water on board and dose myself up with various pills. So let's take a short break now, and we'll carry on at let's go 10 minutes. So 25 past 9, we'll carry on again. Please think of any questions you have in that time, and you can ask me when we jump back on. Cheers. Okay, we're back. Just give me a second, team. Okay. Just changing the sound settings on my computer because there we go. Every time I get an email or something, you guys can't hear it, but it's blasts through my headphones at a horrendous volume, and I shit myself every time. So I just had to go into settings and turn off the sounds. Right, where are we at? Okay, fluorescent lighting. All right. So fluorescent lighting, we're going to go into a little bit more depth than we did on most of the gas discharge ones. You're far more likely to come across this stuff, and you really need to know this quite intimately. It's fairly important. It's saying that, look, fluorescent lights, like all these other types of lights, are becoming increasingly rare. In fact, I believe a few years ago, Philips, who are one of the biggest lighting manufacturers in the world, decided that they would stop manufacturing new fluorescent lighting. Still be able to buy tubes and parts for existing fittings, but they're just not going to make fluorescent fittings anymore because they can produce an LED fitting that'll do the same job and is cheaper to install and lasts longer. So from their point of view, it doesn't make any sense to use fluorescents anymore, or even to manufacture them. It's basically means it's dead technology, right? Fluorescents are going to become like CDs or tapes or records of, I don't know, it's probably some of you don't even know what any of those things are. They just become a technology that's no longer relevant. It still exists, but no one will really use them. However, there are still tens of thousands of fluorescent fittings installed throughout the country in existing buildings, and there's no reason to rip them all out. So ability to diagnose and repair fluorescent lights is really important. Okay, so some of the parts that we're going to see. Ballast. It has two purposes. It's going to limit the amount of current flowing through the electrodes in the tube, much like we saw with the gas discharge lighting. We need to have some resistance in the circuit in order to prevent overcurrent, because the tube itself is not going to provide much resistance for us. So we've got to have a resistor in there, and we use the ballast for that. And in addition, it provides our high voltage surge to ignite the lamp. So it's got two jobs, which is kind of cool when you think about it. The two jobs that the ballast is doing are entirely separate. They're two completely different things, but we can use one part to do both jobs, which is pretty neat. I don't know if that was ever by design or it just happened to be like that, or someone clever's decided that they can do both with it. I'm not really sure, but it's kind of cool that it works like that. So the top here, we've got an inductive ballast. An inductive ballast is just a coil of wire. There's nothing exciting about this. It's a big coil of wire. It has power in through the coil, power back out. So what does that do? Well, for our first use, the current limitation, we know that whenever we put a current through a coil of wire, we're going to create a magnetic field. And as I've talked about before, that magnetic field, the active creation of the magnetic field and maintenance of the magnetic field provides a resistance. So while the coil of wire itself might have a relatively low resistance, if we put a multimeter on it, we're going to get a very small reading because it's just wire. When you connect an AC voltage to it, that magnetic field that's created creates an opposition to current flow. So we will see a resistance there, even though there is theoretically very low resistance in the wire itself. So in that sense, that the inductor, then that magnetic field that it's creating, is just acting as a resistance. So that's our current limitation. The second thing that's happening in the ballast, or the way that it works to provide that voltage spike, is again to do with that magnetic field. When I put a voltage on that inductor, on that ballast, and I create that magnetic field, when I take that voltage away, the magnetic field is going to collapse, right? That makes sense. If I take the voltage off, then I've got nothing maintaining that magnetic field, so it's going to disappear. And that doesn't just disappear into nothing. The magnetic field collapses back into that coil. And just like we've talked about motors, generators, motors, are the same thing, just one's working one way, one's working the other. An inductor, a similar principle is at play here. If I put power onto that inductor, it's going to create a powerful magnetic field. When I take the power off and the magnetic field collapses, it's going to generate a voltage. And it's only going to do that for a very, very brief period of time, obviously, until that magnetic field has disappeared. But when it does that, it's going to release all the energy in that magnetic field very quickly. So as we turn off the ballast, it's going to shoot a voltage spike. And that voltage spike is going to hit the tube, and that's what's going to strike our arc. And we'll have a look at how that circuit works in a bit more detail shortly. We can also get electronic ballast these days. They're going to do the same job, but they do it electronically rather than with a big coil of wire. As you can probably imagine, with as the construction of an inductive ballast, as I've just described it, they're pretty heavy. One of the advantages of electronic ballast is just electronics in there. As I say, I don't know exactly how it works. I don't know what the electronics are doing, but it's essentially doing the same job. In my experience, the electronic ballasts aren't as reliable. They tend to blow out more quickly, which makes sense if you think about the fact that an inductive ballast is just a coil of wire, so it's not like there's much that can go wrong other than the wire burning out. An electronic ballast is obviously a collection of complicated electronic components, and therefore there's a lot more that can go wrong in there. It might be just me, but I still prefer the inductive ballasts, right? They're very simple, they're pretty bulletproof, not much goes wrong, so I would rather use an inductive ballast than an electronic one. All right, here we have our glow starter. So this is our second primary component of the fluorescent light. So it closes. It closes in order to make a connection. So it's a switch, basically. It closes in order to make a connection to allow current to flow to heat up the tube. We'll have a look at how that circuit works in a minute. To heat up the tube, and then as the starter itself heats up, the contacts in there open, which is going to kill the circuit for the ballast. Magnetic field in the ballast collapses, shoots out a voltage spike, strikes an arc across the tube. This we will see when we turn a fluorescent on. You see that as the flash, right? So about a second or two usually after you turn it on, you'll see the fluorescent tube flash. It might flash 2 or 3 times and then it will ignite. So that says when you turn it on, the current flows through the ballast, through the heaters at the end of the tube, and through the starter. starter's closing that starting circuit. As I say, once it heats up for a second, and you'll see the starter itself glow as when you turn the light switch on. When the circuit opens in the starter, we get that high voltage across the fluorescent tube terminals. If it doesn't strike, as in we get that flash, but the arc doesn't take, then the starter will close again because it'll cool down, and that'll restart the starting circuit, and it goes through it again. And once we get enough heat into the fluorescent tube, we can strike an arc across it that will maintain itself, and then then essentially the current flowing through the tube itself will short the starter out of the circuit, and then the starter can just sit there until you switch the light off and on again, and you need it to do its job. So a fluorescent tube is a hot cathode discharge lamp. We looked at the cold cathode discharge lamps like the neon yesterday. This is a hot cathode discharge lamp, which means that we've got heaters at either end of the tube. The electrodes must be preheated to help ionization to start. So we're heating the electrodes inside the tube. That helps to ionize the gas. So gas ionization is the process through which the molecules of the gas, I'm stretching my limit of knowledge in terms of the physics here, but the ionization of the gas is the organization of the molecules inside the gas in such a way that they'll be able to pass current. So a temporary starting circuit through the filament does this, controlled by a starting switch, which are these are things that are contained within the starter. That's what I mean by when it's first started, the switch is closed and it opens. The switch is a glow starter. So yeah, that's our starting switch, if you like. This guy here, the starter. A glow starter consists of a small discharge tube filled with a mixture of helium and hydrogen gas, in which the electrodes form the switch contacts. One electrode is fixed and the other carries a U-shaped bimetallic strip, which flexes when heated and is fitted with a suitable contact at its free end. The whole unit is housed in a plastic cover cap. The starter is designed so that if it fails, you just have to twist it to remove it from its mount and replace it. So you just pop it out, put a new one in. Don't be too concerned about the construction of it, the starter itself. The important thing that we need to understand is a little starting switch, which is going to heat up and open, and then cool down and close, and that gives us our ability to switch on and off the ballast, which, as I said, every time we switch off the ballast, we get that voltage pulse as the magnetic field collapses. Before I continue, is that making sense to people? That concept of the magnetic field collapsing, providing a voltage spike, and that the starter will switch on and off to allow that to happen. I guess those are the two most important concepts, I think, that I want you to understand. Cool. One other person typing. Good. That's the most important thing. Again, we'll look at the circuit diagram shortly, so I should be able to explain that a bit better. But that's the basic idea: ballast, starter, tube. Here we have a power factor correction capacitor. It's connected across the supply and improves the power factor of the circuit as a whole. The circuit has a low power factor owing to the highly inductive choke. Now, we talked extensively about power factor in Module 7. It's a reasonably complicated concept, and so I'm not going to spend a lot of time talking about it now. But suffice to say that, I've said that in the ballast, for example, we have that magnetic field which is acting as a resistor or acting as a resistance. It's not the same as a resistor, right? Because, like I said, we know this. If we put a multimeter on that ballast or any sort of magnetic coil, the resistance that we see will be quite low, but the load that we'll see if we plug it into power is quite high, and that's due to that magnetism. Now, when we're talking about power factor, all we need to say about that for now is that loads that are not resistors, so magnetic loads, inductive loads as we call them, or capacitive loads, both create inefficiency. They will act as resistors, but they're very inefficient, and that's what we call power factor. The power factor of those two things is quite low. Now, the weird but kind of cool thing about an inductive and capacitive loads is they're opposites. So in this case, we could put a capacitor into that inductive circuit, and even though we're introducing more load, we actually make the circuit more efficient because the capacitor and the inductor are cancelling each other out. So we often put capacitors with inductive loads, with magnetic loads, in order to improve the power efficiency of that load. And look, if that makes no sense at all, don't worry about it. We'll cover that in detail later. If that kind of makes sense, or you can just accept what I've said, then that's what our power factor correction capacitor is for. Capacitor will also act as an electromagnetic interference suppressor. It's connected across the starter to prevent electromagnetic interference and help the starter make a clean break when opening the filament heating circuit. So that's, if I go back a slide, yeah, we have our capacitor in the starting circuit, or in the starter itself here. So we'll have a capacitor in the starter circuit, and then the main power factor correction capacitor in the fitting itself connected to the ballast. Ooh. Okay. As we said, a fluorescent tube is a hot cathode lamp, and it's a type of mercury vapor. Ultraviolet light activates a fluorescent phosphor produced. What? That doesn't even make sense. So as we strike that arc, the ultraviolet light that is produced by that arc strikes a phosphorus coating on the outside of the tube, and that's what gives us our light output. It's basically electrons bouncing up and down the tube, let's say that. So we're exciting the electrons by passing a current through the gas, and as those electrons bounce around inside the tube, they're going to hit that phosphorus on the inside of the tube, and that's what's going to produce our light. And that's also how we get different color lights from fluorescent tubes, is using different mixtures of phosphorus. In the video on Canvas for fluorescent lighting, the dude in there had some really quite out there colored tubes, and he talked about the different phosphorus coatings. I can't say I've ever seen, not that I remember anyway, weird colored tubes like that, like red and blue and yellow and green. But obviously we get the different colored tubes to mimic different types of light. So there's your warm white, which mimics the incandescent, and then your white and daylight colors, which mimic the light that comes from the sun. And again, that is the different compositions of the phosphorus coating that is able to give us those different shades of light. Actually, while I think about it, it's just reminded me of something. Hold tight for a second. All right, can you guys see that? We've got a picture of some lights there. Cool. So talking about color temperature, this is what we mean. The numbers there represent the color temperature in Kelvin, which when it says temperature, don't be too concerned about that. It's just mean the different colors of white light. So our typical incandescent is going to be sitting at around 3,000 to 4,000 K. If you buy a cool white or daylight fluorescent, then we're talking about the range of 5,000 to 7,000 K. So that's about the range of colors for the most commonly available lamps that we would use in normal, domestic or commercial situations. Around 3.5 up to about 7K, so in this range here. And you can see, so this is a picture, it's obviously an illustration of what those different lights look like. At that left-hand end, 1,000K, it's quite orangey yellow, and then right up at the 1,000K end, it's starting to look quite blue. And our daylight color is something like around 7,000K. So I quite like that picture. It's a good illustration of what those color temperatures mean. And as I've said a number of times, I think what we should have in our houses is that warm white, 3,000 to 4,000. If you start putting in anything above 5,000, it's going to look really artificial and strange in your house. However, that 5,000 to 6,000 range is pretty common in offices and stuff like that. That's that much whiter light that we typically associate with fluorescent lighting. Although you can nowadays get warm white fluorescent lights as well. It's still the most common. It's the white colors, which is around that 5,000 to 6,000 mark. All right, we'll just go back to the slideshow. No, what did I just do? Oh, yeah, that looks right. We're back on the slideshow, right? You can see the fluorescent lighting slideshow again. Yeah, okay, good. Yeah, so there we go. So the way we get those different colors out of a fluorescent light is to have the different phosphorus, different mixtures of phosphorus inside the tube. Okay. The use of fluorescent powder increases the efficacy of a low-pressure mercury vapor lamp. So it will produce some light by itself. The arc inside the tube will produce some light, but using that phosphorus coating increases the light output and therefore the efficiency of the tube overall. By a careful choice of the chemicals used in the powders, the lamp can be made to emit a light that ranges through most colors of the spectrum. This makes up for the monochromatic light that would otherwise be given out by the electric discharge of the mercury vapor. So as we saw when we looked at the mercury vapor discharge lamp, it's a pretty low spectrum or a low range in the spectrum of color outputs. So this phosphorus coating gives us a better color range. Fluorescent tubes are the nearest simulation to daylight. Fluorescent tubes have a low value of brightness, so you can look directly at them without strain, so they have low glare. So an incandescent, or certainly any type of gas discharge lamp, if you look directly at them, it will hurt your eyes. Whereas a fluorescent lamp, and I'm sure we've all seen this before, you can look at a fluorescent lamp, it just looks like a nice white glow. It's not going to burn your eyes or anything. Therefore distributes light over a fairly large area because it's not a single point of brightness, it's uniformly bright across the length. So the illumination is much more uniform than with ordinary lamps and gives less shadow. Fluorescent fittings are more expensive to install, so there's a cost increase when comparing to a traditional incandescent. However, they consume about 1/3 of the energy of incandescent lamps for a given level of luminance because of their high efficiency. So although they'd be more expensive because there's more stuff there, right? With an incandescent lamp, all I need to do is connect the voltage and it goes. With a fluorescent, I have to have a ballast and a capacitor and a starter and a big fitting and all that stuff. So it's more expensive, but generally they're cheaper in terms of total life cycle, as we've discussed previously, because the energy costs and ongoing maintenance costs are going to be less compared to an incandescent lamp. Okay, how does it work? We'll skip that and go straight to the picture. Yeah, okay. That's not a great picture. Have we got a better one? No. Oh. Bugger. Sorry, I switched that off. Let me try again. That's not what I want. Oh, I've broken it. What are we seeing there? That's not the slideshow, is it? Why not let me open the slideshow? So Lars just gonna entertain us with pictures of ninjas while I try and fix this. Should have actually broken it. I can't share that slideshow anymore. I don't know what's gone wrong. Okay, I'm just going to leave the meeting for a second and then I'm going to jump back in. I just think I just need to reset it. So hold tight there. Okay, can you guys see that now? Just done it a different way for some reason. It didn't want to show the slideshow anymore. Okay, cool. Right, where were we? Okay, so let's have a look at and see if we can figure out the circuit here. So we've got our, can you guys see my mouse on this one? Shit, okay. So you'll just have to follow along. I wonder if there's a way for me to turn the mouse on. Oh, this is ridiculous. I can't go back. There we go. Okay, you can't see my mouse, so you just have to follow along as best we can. So down in the bottom right corner, we've got our power coming in. You've got active and neutral there, obviously. If you follow the bottom wire, the active one, follow it in the direction of an arrow, it's going to go through the ballast. So it's just going through the ballast in series. So that, again, that's just our coil of wire. So that's creating a magnetic field as the current flows through the ballast. Exits the ballast, and it's going up to the tube. At the end of the tube, we've got a little heater element in there. So it's just a little coil of wire that's going to heat up. And again, that's in series, so it's going to go through there and then back out the heater element up through the starter. The starter is closed at this point, right? So the starter is just acting as a closed switch. It flows through the starter, through the coil at the other end of the tube, and then back to neutral. So at this point, all that's happening is the ballast is charged. There's a magnetic field in the ballast, and the two little coils at either end of the tube are heating up. And you'll see those. You see this especially if you try and run a fluorescent tube with a faulty starter. Often you'll just see the ends are glowing and nothing happens. That's just the heater coils at the end of the tube. So the heater coils are running and they're heating the gas inside the tube to help ionize it. Once the starter has heated up for a couple of seconds, the bimetal is going to open. That's going to collapse the circuit of the ballast. So if you look at the starter there, you'll see that once that starter is open, the whole circuit is broken, right? At the moment, everything is in series. We're just going in a series circuit through the ballast, through the heater at one end, through the starter, through the heater at the other end, and back to neutral. So when the starter opens, that whole circuit is going to be dead. There'll be nothing happening. When we do that, the magnetic field in the ballast is going to collapse, and that's going to shoot a high voltage. As that magnetic field collapses, it's losing its energy and pushing it back into the circuit. So it's going to shoot a high voltage up to the heater coil at one end of that tube, right? And then it's going to strike an arc between that electrode, the heater coil, to the other end of the tube, the heater coil at the other end. So the current is going to flow through the tube itself from one coil to the other. Those are our electrodes. And then obviously from that second coil back to neutral. If the arc strikes and maintains, then we're going to get a continuous flow of current through the tube. And now we don't need the starter anymore. If the starter remains open, it doesn't matter because I've got current flowing through the tube itself from one end to the other. Once that happens, then the starter's just going to sit there. Even if it closes again, it won't do anything because it's going to be shorted out by the current that's flowing through the tube. The ballast at this point, because current is now flowing again, it's flowing through the tube, so the tube itself, the gas in the tube is making the circuit. The ballast will then recharge and create that magnetic field again. And now the field's not going to collapse because the current will continue to flow. So then the ballast is just acting as basically as a resistor. That's what we talked about as current limiting. So there's basically a short circuit through that tube. So the resistance then is the ballast itself, the magnetic field in the ballast. And now the tube will just sit there and operate. If that starter opens and the arc fails to strike or fails to maintain, then you'll see that flash. This tube will turn off again. The starter will cool down, it only takes a second or so, and when it recloses, then the starting circuit starts again. Ballast charges up, the heaters start at the end of the tubes, the starter switch will stay closed for a couple of seconds, and that allows the heaters at the end of the tubes a little bit of time to heat up and heat that gas up, and then once the starter opens again, then we're trying to start that arc again. And each time that happens, obviously we're going to get a little bit more heat into the tube, and that's why when we turn on a fluorescent, you'll often see it flash a couple of times, because that's the heater tubes heating up, starter opens, we strike the arc, it doesn't maintain itself because maybe we haven't got enough heat in the tube yet, so starter recloses, heaters heat up again, so on and so on, until we get enough heat in that tube that's going to strike the arc and maintain it. Does that make sense? So it's kind of a tricky process, and I think actually a lot of people don't understand it very well. But once you understand what those components are doing and what they're for and how that circuit is supposed to operate, it's actually not too difficult. It's fairly simple. And understanding how that circuit works is really, really important for being able to fault find and repair these lights, because then we can start to tell, well, if it's doing this but not this, then that must be the whatever component. Because if I understand how the process is supposed to work, then I can observe what parts of the process are working and what parts of the process are not. For example, if I just see the ends of the tube glow and nothing else happens, we get no strike, just the ends of the tubes are glowing, that probably tells me my starter's faulty, because the starter is staying closed. It's not opening. When the starter opens, that's when the magnetic field on the ballast is going to collapse. And that gives me that strikes across the tube. If the starter is just holding closed, then it's just going to maintain current through the heating circuit, and the ballast magnetic field never collapses. So it'll just sit there with the ends glowing. And quite often you'll find that if the tube is doing that, you could just get up there and pull the starter out, and that might actually strike the arc, because when you pull the starter out, you're doing the same thing as if you were to open, if the starter contact's opened. So if you've got a faulty starter that's just held closed, it'll just sit there with the ends of the tube glowing. If I pull the starter out, it will usually start the tube itself. And if that happens, then we know we've got a faulty starter. So we just put a new starter in there and we should be good to go again. Okay, so just a little bit more on that starter then. So as the bimetallic strip cools down, the switch contacts open within a second or two. So this is at the start of the circuit. When I apply power, we're going to get a couple of seconds where current is going to run through those heating coils in the tube, through the starter acting as a closed switch. When that circuit breaks after the starter opens, that's producing that high voltage surge because of the collapsing magnetic field in the choke, or choke is another name for ballast. Surge of up to 1,000 volts is large enough to cause the tube to strike. If the tube fails to strike at the first opening of the starter contacts, a discharge passes again, and the cycle of operation is repeated until the tube strikes. A small capacitor is fitted across the starter contact to suppress radio interference and give cleaner brake to help starting. A large capacitor is connected across the circuit as a whole to correct the low power factor caused by the ballast or the choke. We talked about that. This capacitor corrects the power factor from about 0.5 to about 0.85 lagging. All that means is that's just the efficiency that we'll see. So using that inductor without a capacitor, we're going to see about 50% efficiency. And then putting the capacitor in there improves our efficiency up to about 85%. Okay, are we happy with that? So we're cool with the basic process of how fluorescent light works. Cool. Okay, let's take another break so I can stop talking for a minute, rest my poor voice. So let's have smoker time. It's come back at 10:30, and we shall continue. We're nearly to the end of this one, and then the next two that we'll do today are much simpler than this. So take a pause there. I'll see you in 25 minutes. Okay, I'm back. Are we ready to carry on? Is anyone there? All right, cool. Okay. We got 4 people, so that'll do, I suppose. Looks like the 4 most important people anyway. All right, we're nearly finished on this one, so we'll just give this a burst and we can move on. So stroboscopic effect. So this is just something that we need to know about gas discharge lighting in general, I guess, but fluorescent lighting in particular. When discharge lamps are used on an AC supply, they produce a pulsing light. It's therefore unwise to illuminate moving machinery with these lamps because this light pulsing sensation can cause an optical illusion called the stroboscopic effect. If a discharge lamp is used on an AC supply having a frequency of 50 Hz, the lamp gives 100 flashes of light per second. So that's 1 flash on the positive half cycle, 1 on the negative. But the human eye cannot follow such rapid variations, so the light appears to be of constant intensity. So it will look to us like it's just one continuously lit lamp. A wheel that is rotating at 25 revolutions per second and illuminated by such a pulsating light, if we consider 2 successive spokes on this object, A and B, A being the leading one, during the flash of light, both spokes are viewed in a particular position, and by the time the next flash arrives, B has come to the position that previously occupied by A. The wheel then appears to be stationary. If the speed were a little less than 25 revolutions per second, B would not quite reach A's original position, and the wheel would appear to rotate slowly backwards. Above 25 revolutions per second, the wheel would appear to run slowly in a forward direction. You'll often observe the stroboscopic effect when viewing a turned wheel in a television or cinema picture. All right, so what we're talking about here is if a wheel is rotating at the same speed that our light is flashing at, and the reason it talks about a TV picture there is that on the television, the camera is taking a number of pictures per second. That's how a camera works, right? It takes a bunch of pictures really fast and then knits them all together, so we see a moving picture. And in the same way that you'll see like, for example, a car accelerating on TV, you'll see the wheel spinning forward and then it'll start to slow down and stop, and then it starts to spin slowly backwards and speeds up, and then it will stop and then it'll go forward again. These are all stroboscopic effect. If the camera frames per second is the same as the speed of the wheel, then it'll look as though the wheel is still, because each time it takes a picture, the wheel is in the same position as it was before. So fluorescent light can do the same thing by flashing at a certain frequency. If we have something that matches that frequency, or it's matching at a multiple of that frequency, it can give an effect where that wheel looks like it's staying still. If we consider any kind of rotating machinery, such as a lathe or something like that, you can get that same effect, and this can be quite dangerous, obviously, because if the lathe looks like it's sitting still when it's not, and I stick my finger in there, it's going to have my finger straight off. So, methods to limit the stroboscopic effect. Stroboscopic effect can be a big danger for people working with moving machinery. Note that the commonly used fluorescent tubes produce this effect. You have to use one of the 3 following installation methods to reduce stroboscopic effect. Install pairs of fluorescent tubes with special twin tube ballast that cause one amp to take a leading and the other to take a lagging current, so producing a time delay between the light pulses of each tube. So we're just putting them slightly out of phase in order to make that they're flashing alternately. Connect adjacent single tube fittings on different phases, because our phases are on a 3-phase system, the phases will be out of sync with each other, and therefore that flashing is going to come on at different times, and so we can limit that stroboscopic effect like that. or we can mix in some incandescent lighting with our fluorescent, so that we always have some light when the fluorescent is flashing on and off. The incandescent is still lit, so we're not going to have that light dark, like I said, even though our eyes can't pick it up. It's that light dark flash of the fluorescent which is causing that strobe effect. So looking at the fluorescent, the color rendering, this is an example of two slightly different types of phosphorus, but you can see on each of them that we've got a pretty good approximation of the color spectrum. The first one there's got a pretty smooth curve going up from red through green at the peak, and then coming down, a couple of spikes in the blue spectrum, and then the curve coming down into the white. The second one here mirrors that, but without perhaps the smoothness. It's just got spikes, but again, we can see that this one looks quite similar to the metal halide that we looked at. We've got spikes there at all the major points on the spectrum, and therefore that's going to give us a fairly uniform light output, or at least it will appear fairly uniform to our eyes. So again, that having a good output across the color spectrum means that it will give us pretty good color rendering, so it'll appear as a fairly natural kind of light. Okay, a summary. A glow starter consists of a small discharge tube filled with a mixture of gases, helium and hydrogen, in which the electrodes form switch contacts. Its two functions are first to close the circuit through the filaments of the fluorescent lamp, and then after an appropriate time to open the circuit quickly. In the glow starter single tube fluorescent lamp circuit, the ballast or choke serves two functions. It limits the amount of current flowing through the electrodes and the tube, and provides a voltage surge of high enough potential to initiate a discharge. That's when the starter opens and the magnetic field collapses. Two capacitors are connected in the circuit. One is connected across the supply to correct power factor, and the other is connected across the starter to prevent EMI and to help the starter make a clean break when opening. Stroboscopic effect produced by fluorescent lamps can be reduced by operating pairs of tubes from special twin tube ballasts, connecting an adjacent single tube fittings on different phases, or using a mixture of incandescent fluorescent lamps. Luminaires can be classified as according to how they distribute light, direct or indirect. Gas discharge lighting is where light is produced via flow of electric current through a gas. The gas discharge lamp emits light over only part of the spectrum, as we saw on all of those gas discharge lamps that all have a limited spectrum. Some of them are better than others, but none of them are perfect. That's that. That is the end of that slideshow. That is gas discharge lamps completed. Do we have any questions, any general questions about gas discharge lamps? Nothing at all? Silence. That's a great question, Raymond. Yes, you are correct. So in a the compact fluorescent, the little spiral ones or whatever that you just screw into a normal household fitting, it doesn't have the ballast in the starter in the same sense as what we were looking at. But it has an electronic system that'll do the same thing. So if you smash one of those open, you see in the base you have usually the little white base, which is quite big. So all the electronics are contained within there that are doing the same job as your ballast and starter in a traditional fluorescent tube. As I said before, I prefer the old style ballasts ballast and starter system because I think they're a bit more reliable than the electronic ballast. But if you go back, I've already closed that slideshow, but if you go back in that slideshow, it had a picture of an electronic ballast in there. So essentially all the stuff that's in that electronic ballast are smashed down into the base of your compact fluorescent that you put into a normal light socket at home. So yeah, the short answer to your question is yes, it is. It's built into it, and the slightly longer answer is electronics and stuff in there that do that job. But yeah, great question. Yes, all of that stuff is built in. Nice one. At least I know one person's paying attention, thinking about what's going on. All right, anything else? Does that answer your question, Ray? You happy there? Excellent. Good question. Appreciate it. Anything else from anyone else? No, okay, we'll leave that there. All right, let's move on to LED lighting then. So we've got two more that I want to do today, LED and recessed lighting. They're both pretty straightforward and simple, so we'll get through those pretty quick. This one we should be able to get done before lunch, and then we'll take a break, and the other one should only take about an hour. So again, we'll probably finish by about 2, which will leave you some spare time to do all those tests, because I know you're just itching. All of you are just itching to get those tests done, aren't you? It's our favorite thing. Okay, now I will say, before we start the slideshow, that obviously our content is not updated like every 6 months. Most of these slideshows tend to be in rotation for 4 or 5 years before they get updated, which for the vast majority of things are fine. If we look at the last slideshow, nothing much has changed with fluorescence and discharge lighting for quite some time. So the content within there, the information is likely to be just as good now as when it was first written. Unfortunately, the same can't be said with LEDs. LED lighting has progressed rapidly. I mentioned it earlier that the advances in LED lighting in terms of the colors, efficiencies, price, all of that sort of stuff has changed a lot, even over the last 5 to 7 years. So some of the stuff that's in this slideshow might be a little bit out of date, and I will try to identify that where I can. I mean, the basic operating principles remain the same, so the majority of this will be fine. Okay, LEDs. Applications: indication lights on devices, small and large lamps, traffic lights, large video screens, signs, street lighting, although it is not widespread, residential, and shop display. So, well, pretty much everywhere, right? The LEDs are becoming more and more common, although it says there street lighting, this is not widespread. I tend to look at these things as I drive around, and I believe that certainly any new street lights that you'll see installed now will be LEDs. I don't think they're replacing old style gas discharge lamps and street lights. Generally, they swap them out for LEDs. So it won't be long. I mean, like I was talking about earlier, that process of replacing streetlights is probably ongoing it's a multi-year process that they do. So it wouldn't surprise me if the council has a plan for that over time they'll swap out all the gas discharge lamps for LEDs. But I would say that this particular slide is a little bit out of date in the sense that the usage of LED lighting is probably much more widespread now than when this was written. So an LED is a small light that easily fits into an electric circuit. These lights do not get hot, and they are illuminated by the constant movement of electrons located in the semiconductor material. It's a diode, so it's a semiconductor. The average life of an LED is around 50,000 hours, and it surpasses the life of typical incandescent bulbs by several tens of thousands of hours. Nowadays, you can find LED lights in a variety of applications, including TVs. Yeah, so the most important point to note here is that 50,000 hour lifespan. As I have alluded to, A lot of the information that we'll see in this slideshow, one of the reasons we should skim through it pretty quickly is that I've talked about LEDs constantly as we've been talking about other types of lighting, right? And the reason that I've done that is because they're so much better than everything else out there in almost every respect that it's almost ridiculous to talk about those other types of lighting without basically mentioning as we go that there are other types of lighting, i.e. LEDs, that are superior in almost every respect. So it's really important that we understand all of those other types of lighting in the context of LEDs that are in the process of making all of those basically obsolete. So 50,000 hours there. If we think back to the gas discharge lighting, I think the longest lifespan we were looking at there, I think was maybe the high pressure sodium was 16 to 20,000 hours, something like that. So 50,000 hours is way beyond that. Again, if we remember our incandescent lamp, which, the incandescent is the standard for all types of lighting for a long time, we're getting 1 to 2,000 hours. Of course, that one random lamp at that fire station that we looked at would be the glaring exception, 120 years. However, other than that one, 1,000 to 2,000 hours out of an incandescent, 50,000 out of an LED means that we're getting multiples times greater lifespans. And if we think about, as we discussed earlier, average usages, remember I said that 2 to 3 hours a day in most places in your house. So perhaps 1,000 hours in a year, and in the very high traffic areas in your house, you might be 1,500, possibly 2,000 hours at the outside, but unlikely. So even in those cases, 2,000 hours a year, your LED is going to be lasting 25 years typically, which is crazy when you think about it, right? And the fitting itself is likely to fall apart before you have to worry about the light not working. Yeah, I think that's all I'll say about that. The LED stands for light emitting diode, and it refers to a special type of diode that is specially created to provide light when electricity passes through it. These diodes are basically semiconductors that are used to control the direction of electricity flow. We've looked at diodes a little bit. It's a small electronic device that allows current to travel in one direction, but not in the other. And those are used, a diode is used for many purposes in electronic circuits. We'll deal with that a bit more when we come to our module that focuses specifically on electronics. The upshot here is that at some point somewhere, somebody discovered a certain type of diode, or constructing a diode in a particular way creates light. And it creates light in a way that consumes very little electricity. So for a long time, LEDs were it's very much what we're looking at, this picture here with the red, green, and blue ones. They're just the little indicator lamps that you see, on your TV or anything that just has a little light to say whether it's on or not. And that's what we used LEDs for. They weren't particularly bright. Initially, they were only red. I think for about 30 years after LEDs were first invented, you could only get red ones. Hence, if you think back to your 1980s or 1990s style clock radio, that, well, I don't know, maybe some of you are too young to ever have even had those. But maybe your nana's still got one next to her bed or something. But you remember those clock radios always had the red numbers. That's because they were using red LEDs, because only red LEDs existed. So over time, people have figured out a way to make much brighter LEDs, to obviously make them in different colors, blues, greens, so on. And then the big innovation that made LEDs become viable as general purpose lighting as opposed to colored indicators was that we figured out how to make white LEDs that were very, very bright and therefore can be used for general illumination, which is where we are now. Average light emitting diode does this through what is known as a p-n junction formed of a p-type semiconductor, which contains positively charged carriers, and an n-type semiconductor, which contains electrons. The connection between these two types of semiconductors is known as a p-n junction. These junctions are the building block of every semiconductor electronic device. Yeah, so this is general to any type of diode, or in fact any semiconductor such as a transistor, triac, diac, anything like that. So what that means is that when we put a voltage onto a diode, electrons can jump across from the N layer to the P layer, but they won't go back the other way. So hence we get current flowing in one direction and not the other. That's a very simplistic way of looking at it, but close enough. And then, as I said, the LED is a type of diode that when this process happens, it will also emit light. And here we have it here. Light emitting diodes are modified in order to produce a form of light radiation, and the electrons from the N-type semiconductor simply connect to the carriers in the P-type semiconductor. So that's, we've got electrons jumping across the junction between the two different types of semiconductor material. The semiconductor material that we're talking about in this case is silicon, right? So when we talk about, people talk about silicon chips and stuff like that. It's because silicon is a semiconducting material. So we can construct it in such a way that you put a p-type and an n-type together and you get that junction, which will allow current one way, not the other. It's possible, flow of electricity is unidirectional. It is possible only from N to P and not the other way around. When the junction is formed, electrons located in the diode change their state and start to emit photons. It's light particles. Electrons change their orbit by moving from a higher orbit to a lower one. When they do that, they automatically lose energy in the form of light. The more energy is lost, the more powerful the photons of light. This is when the color starts to change and light is being emitted by the LED. Neat. So in simple terms, you put power on the LED and then complicated physics stuff happens and light comes out. There you go. LED lights are designed to emit one color of light, but over the past years, manufacturers have come up with bi-colored light bulbs, and the most popular colors at the moment are red, green, and blue, although there are a variety of colored LED bulbs available on the market. In the case of large LED displays, manufacturers use a combination of LEDs that aim to give a wide range of colors. These displays use a 3 LED pixel. For general lighting, such as in homes or offices, the LEDs are designed to give off a white light. Yeah, so this slide's probably a little bit out of date, right? It's talking about red, green, and blue lamps, which are kind of redundant. In TVs, it says there a 3 LED pixel. So if you go back to the old cathode ray tubes, the old style televisions, the big ones, it's a giant electromagnet in the back of there in a vacuum tube. So what's happening is the electromagnet is accelerating electrons which strike a phosphorus coating on the front of the screen, much like a fluorescent tube. And when the electron hits the screen, it's going to emit a color depending on where it strikes it. So you have red, green, and blue phosphorus on the screen. So when it strikes the red part, it emits red, so on and so on. So all of the colors on that cathode ray screen are made up of the red, blue, and green phosphorus. And if you looked at the screen really closely, you could actually see that. It looks all red and green and blue dots. Yeah, well, we're not here to talk about cathode ray tubes, but it's interesting nonetheless. So where LEDs have replaced cathode ray tubes is that we have very tiny LEDs grouped together, a red, a green, and a blue. And so the picture is made up by lighting each of those at the appropriate time to create a picture. So the combination of red, green, and blue light can make any other color of light. So we just have to light up the right colors in the right places, and you'll see a full color picture. But at its heart, there's only three actual colors of LED in the screen that are doing that, and they're very, very tiny. It's sort of, says there are 3 LED pixels, so every pixel is 3 LEDs. That could be either of those 3 colors. And I believe that when we each generation of higher definition screens, 720, 1080, what are they putting out now? The 4K screens are 2580 or 1920 or something like that is the screen resolution. That's how many pixels, so how many collections of the red, green, and blue LEDs are within the screen. So I'm pretty sure, don't quote me on this one, but I'm pretty sure that as display resolutions get higher, that's because people are discovering ways to make the LEDs themselves, the individual LEDs, smaller and smaller, so you can pack more of them into a screen. Looks like somebody's about to ask a question, so I'll pause for a second. Yeah, there's probably a lot of soldering. Well, when you say that, Ray, it makes me think that it's a good point. I don't think that my LED screen TV is made up of a big electronic board with tens of thousands of tiny LEDs soldered onto it. I don't actually know how they do it. It makes me want to rip apart a TV. If anyone's got a TV that they don't want, bring it into class one day and we'll rip it to bits. See if we can find the LEDs. Oh yeah, we should do it with the one in the Class 810. I can't get this stupid thing to work. So we might as well just rip it to bits. Oh, you threw one out, Jade. How dare you? Actually, since we're talking about it, anytime any of you guys have any appliances that you're throwing away or anything electric, feel free to bring that into class, because I'm certain that we'll be able to rip it to bits and learn something out of it, even if it's only looking at how it's put together. I'd be more than happy to do that in any of our practical classes. Pulling things to bits is obviously the best way to figure anything out, really. You're more than happy to do that. Okay, is that all the questions? Looks like somebody's typing and then stopping. Okay, move on. All right, color temperature. LED lights are available in different color temperature ranges. Most of them provide a white light in different shades, from soft white, so that yellow tinted incandescent, to a bright white like a fluorescent tube. Soft white lights are best if used indoors for task lighting, while bright white lights are often recommended for outdoors and are well matched for accent lamps. Yeah, so we saw that picture that I brought up earlier with the different color temperatures. Yeah, remember there. So you can pick up LEDs off the shelf that span that range from that 3,500, which is quite a warm yellowy white light, up to 5,000 and 6,000, which is that white daylight colored light, and even a little bit beyond that, which is starting to be blue tinged light. Again, I've mentioned it before, but don't put daylight or cool white colored lights, whether they're LEDs or fluorescent, into your house, because it looks stupid. Get the warm white ones. And most of the time, they're standardized colors. So if you go and look at LEDs, bulbs on the shelf at the supermarket or something, you'll see they'll either be labeled usually with warm white, cool white, and daylight. Or some of them might only have warm white and cool white, or warm white and daylight or something. So warm white are the ones that we want at home. Don't buy the white or daylight ones. Oh, I mean, if you prefer it, be my guest, but I wouldn't recommend it. Warm white is the one. That's the That's the color that mimics an incandescent lamp. Color rendering. Depending on where the LED light bulb is situated in the color temperature spectrum, there can be all kinds of colors: blue, green, red, yellow, and shades of white. Another aspect of the LED light color is the color rendering index. These bulbs give great color rendering, which is the capability of a bulb to display the true color of objects, which we have talked about extensively with the discharge lighting. The best LED lights produce a light whose color rendering index is about 85%, so there's a great diversity in these LED bulbs. Usually the greater the CRI value, the greater the number of objects illuminated by the LED bulb, which will appear natural. Yeah, and look, I think that's improving all the time as well. So again, the LED light is going to be superior to certainly all of our gas discharge lamps, certainly superior to the fluorescent, and on par with an incandescent in terms of the color rendering ability. So whilst we have seen, when we looked at the gas discharge, we saw that there are some of those lights that may rival LEDs in terms of their output per watt, the efficacy. Some of them last a very, very long time. None of those lights that we've looked at, whether fluorescent, gas discharge, or incandescent, none of them can match an LED for the overall value. You know, they're efficient, they produce a great light, they're reasonably cheap or becoming cheaper to install, and they last for almost forever. So across all of those things, while you might get one or two different types of lights that might beat an LED on one or two of them, across the board, they're superior in every other respect. And that's why they're going to make all those other things obsolete, right? So incandescent's been around forever. Fluorescents have been around for a long time. Different types of gas discharges have been around for a long time. But we've always had all of those types of lights, and they're suitable for different purposes. Incandescent works better in your home. It's inefficient, but we're not using a huge amount of lighting in our home, so they're not super expensive to use. So the value of the incandescent, the color of the light, and the color rendering made the incandescent more appropriate for in homes. The fluorescent is far more efficient, has that more uniform spread. So those advantages made it good for lighting large indoor areas, offices, and that kind of thing. There were some downsides, like the color rendering, which meant you didn't want to use it in your home, but in certain applications it was better. The gas discharge, they obviously last a lot longer, and they're incredibly efficient. So in areas where we want a lot of light at low cost, and maintenance costs were important, so we're talking now about factories, we're talking about street lights, the gas discharge lights were more useful than incandescent or fluorescent. I mean, we're certainly not going to light a workshop with incandescent lighting or use incandescent lighting in the street light. So all three of those different types of lights then had their various advantages, which made them useful in different places. Hence, we've got those three different technologies which were still used and have been used for a long time. And what we're seeing now is that LEDs, because they're superior to almost superior to every one of those technologies in every respect, they're becoming the go-to lighting type for all of the different applications that we use those different types of lights before. So as I say, there might be some small advantages remaining to particular types of lights. Overall, the LEDs are so much superior in every respect that they're just going to make all of those things obsolete. We're going to go through a situation or a world where we have multiple different types of lighting technology for different purposes, to one where we just have one type of light because it's better than everything. Which I know you guys probably wonder why I crap on about this so much, but genuinely, as an electrician and someone who's interested in this sort of stuff and technology and all of those things, that's such a massive breakthrough that I've had to use all these different things to do different jobs, and then along comes a technology that just goes, nah, we're just going to use this one thing. That'd be almost like, if you think of cars, right? You have different types of cars that do different things. You have trucks to carry loads, buses to carry people, vans to carry work stuff around, cars that we drive around, all of those kind of things. Different types of cars for different things. But so the advent of LED lighting to make all of those other ones obsolete would be like if you could buy, a truck that handled like a car, and it was cheaper to run. It just did all of the jobs that every other type of vehicle traditionally did. So then we could all drive around in trucks, and we could carry massive loads, but they would be as fast as and handle like a car. So we just wouldn't need any other type of vehicle anymore. You wouldn't need a truck and a car. You just have one vehicle that does both jobs. So to me, at least, as a bit of a nerd about this kind of stuff, having that single technology overtake everything else, it feels like a kind of a similar situation. And if you're still sitting there scratching your head, wondering why I give a shit, I don't know what else to tell you. I just think that's really neat. What do we got next? Performance. LEDs have a outstandingly long lifespan. Some can last up to 50,000 hours, and that's increasing all of the time. Whoops. That's increasing all of the time. So they're making LEDs that will last longer and longer and longer. So it makes them an ideal option for hard to reach lighting. Well, yeah, I guess if you're still coming from the point of view where you need different types of lighting, then this is an advantage for LEDs. I can install a light somewhere, and then I don't need to get access to that thing again for a long, long time. So in terms of maintenance costs, if it's difficult to access a certain thing, LED is going to be a good idea. LED lamps have a good lumen quality with a luminous efficacy between 60 and 70 lumens per watt. I think that's well out of date. That is actually well out of date. Hold fire there. I'm just going to do a quick Google. Actually, why don't you do this along with me? And let's see if we can identify the lifespan of a modern LED light. Because 60, sorry, not the lifespan, the efficacy. If you look at that bare number there, you would say actually most of our gas discharge lightings are more efficient than the LED, and I don't believe that is the case. So just chucked a link in the chat there to the Wikipedia page on luminous efficacy, and that's it's got a table in there with the various lamp types and what the average efficacies are. So a 230 volt incandescent, different efficiencies depending on the size. But it says here that a 100 watt tungsten incandescent used on 230 volts is about 13.8 lumens per watt, which, remember when we talked about incandescent lights, I didn't even know if that was yesterday or last week, we got a similar figure, 13.8 lumens per watt. If we look at our gas discharge lamps here, the highest one was the low pressure sodium. So this is telling me that I get 100 to 200 lumens per watt on a low pressure sodium lamp. High pressure sodium 85 to 150, metal halides 65 to 115. So they're all pretty similar to what we saw in our slideshow. LEDs, $75 to $120. 21.5 watt LED retrofit for a T8 fluorescent tube, so a replacement tube. 172 lumens per watt. 172 lumens per watt puts it as quite a bit ahead of even the best gas discharge lights. And it also notes here, theoretical limit for a white LED with phosphorescence color mixing. The theoretical limit is 260 to 300. Now, I suggest that means that people have managed to do that perhaps briefly in a laboratory setting, but maybe they haven't been able to replicate that in production yet. But that also tells me that the efficiency of our LEDs are going to increase and become better and better. So the average number it's giving me there is 75 to 120, which is significantly superior to the 60 to 70 lumens per watt that I'm seeing here. And that lines up with my own rough baseline figure in my head that an LED is about 10 times more efficient than incandescent. It's not quite, but perhaps 9 times. 9 times more efficient than an incandescent. I'm pretty sure that if you pick up a LED bulb at the supermarket or Bunnings or something, and you have a look at the box, it'll tell you, obviously it'll tell you the wattage, but often it'll tell you the lumens as well. It tells you the lumens. An old incandescent didn't used to tell you the lumens, but nowadays the LEDs do, because people don't understand that a 10 watt LED can be equivalent to a 100 watt incandescent. So it actually has the lumen output on there, and I'm pretty sure LEDs that range maybe from 9 to 11 watts will be pumping out around about 800, 900 lumens. So again, yeah, probably about 90 lumens per watt, or about nine times more efficient than an incandescent. Sounds about right. I encourage you to have a look at that. Have a look at that when you see an LED on a shelf somewhere. Pick it up and have a look, see what it says. Cool. So just while I'm saying this, although I'm actively contradicting some of the stuff that's in the slideshow, because as I said, some of it will be a little bit out of date, just be aware if it does ask you a question about this in the test, it's going to be the values that were given in the slideshow, right? Not random values I found on Google. Safety concerns. The biggest concerns about LEDs and eye damage revolve around the brightness of the lights, UV exposure, and the blue light emitted. It's true that some ultraviolet and infrared LEDs exist, but they are not available for consumer use. The LEDs that are available for commercial and residential use produce UV light that is well below any threshold that could be a problem, and they emit even less because that UV light is converted to white light by the phosphors in the lamp. So inside the LED, we're getting a similar thing going on to what we have in the fluorescent, right? So the LED itself will emit light, but then we have a coating inside the plastic housing of the LED, a phosphorus coating like in a fluorescent, that's going to change the color of that light for us. There's no question that LEDs are bright, but that's not a bad thing. The trouble comes in when the wrong light or a too bright light is used where it shouldn't be. You must match the light to the intended use or you'll cause eye strain. And look, in most cases, you'll find that LED bulbs, if you get a LED bulb looking thing like that is made to mimic incandescent bulb, they'll be frosted, so you get a bit of diffusion there. I've got one. I pulled one apart last year at some stage, but we'll rip one apart next time we're in the workshop. Those little plastic ones that we use, that we've been using to test our lighting circuits on our projects. You can just cut the end off there, and you can actually see it's just a flat surface inside with all those just little LEDs on them. It's nothing complicated there, just tiny little, incredibly bright LED lights. And so we just have that. If you remember the ones I'm talking about, you have that half circle of clear plastic. It's just frosted to give us that diffusion, which takes away the brightness of each of those individual lamps. Blue light LEDs appear bright white or even blue to the eye, which can cause eye strain to those with light sensitivity. It's not dangerous, but if these colors are irritating to you, stick to the warmer colored LEDs, which are rated with Kelvin or a K value of under 3000. So that's going back to those color temperatures that we looked at before. Yeah, I mean, it's just a general thing, I guess, that happens in the world. We talk about the blue light effect of looking at screens and stuff like that. You can get glasses these days, like when I buy prescription glasses, there's an option where you can get blue light filters on them, which just tones down the colors of, or the color of blue and white light. But unless it's irritating to you, it's not damaging. Installation safety, lighting requires working at heights. So be sure to use the correct ladder or platform for installation or repair. I don't know why this is in the, specifically in the LED, slideshow, because it's something that pertains to all types of lighting. Nevertheless, working at heights, safety should be observed when installing or maintaining lights, whether they're LEDs or anything else. All right, converting existing lighting. If you're adding LED lamps to fixtures on dimmers, make sure to select dimmable LEDs and plan to replace your dimmer switches too. Using dimmable LEDs is not as simple as just screwing them into your existing fixtures. Dimmers designed for standard incandescent bulbs will often cause LEDs to buzz or hum annoyingly. There are a range of lamps installed in homes and offices with different fittings. The fittings must be matched. If unsure, the best way to do this is take the old lamp to the wholesaler or lighting supplier. If you're replacing downlights or spotlights, take one out and see if it has pegs or pins. If it has pegs, that's main voltage, GU10, and it's no problem to change. If it has pins, this is low voltage. It's a little bit more complicated, so you may need to change the driver. Yeah, so in general terms, lighting manufacturers are designing lights, LED lamps, to be one-for-one swaps. The driver, so an LED requires a driver, right? You don't just put 230 volts on an LED. Typically for LEDs, the forward bias voltage, or the voltage required to make it transmit current, is something like 1.8 to 3.6 volts, I think. So very small voltage. And as with the gas discharge lighting that we looked at, the actual resistance across an LED when it's transmitting current is almost nothing. So even if I had a 2-volt power supply, I don't want to put that directly on an LED because it's basically going to be a short circuit and it'll blow up. So we've got to have current limiting in there. We've got to have something to reduce the voltage down. We've got to have something to limit the current that goes through the LED. And that's basically what our LED driver is doing. However, when you buy a bulb off the shelf, the LED, the driver to the LED is essentially integral within it. Much like the question that Ray asked a few minutes ago about a fluorescent tube, the same applies to the LED. All the driver and electronics we need are in there. So as long as I get something that will fit into the same fitting, as in the socket end, or the end that goes in the socket is the same as the one that I'm replacing, then everything else is going to be the same. Nobody's manufacturing a LED bulb that has a standard bayonet cap fitting, but it actually operates off 12 volts. That would be outrageous. So you buy one that looks the same as the one you're taking out, and you should be fine. Even if you're talking about the low voltage 12 volt MR16s, you buy an LED bulb with the MR16 pins on it, and it's designed to take 12 volts. And again, it has all the electronics inside there to change that 12 volts into the form that it wants for the LEDs. So it's not really an issue. Perhaps a few years ago, maybe this is something you had to think about, but nowadays they figured out that we just make them so they match one for one and straight swap them. It kind of surprises me a little bit, to be honest. If you look at like the new style downlights, LED downlights, we've got a few in the workshop that we can look at if you want to. They are, with the LEDs and the downlight, a single thing, so it doesn't have a replaceable bulb in it. It's just a fitting with LEDs inside it, and you put power on it and you mount it. Again, they usually come the same size, same physical size as the incandescent downlights, so you can retrofit them, or you can fit them into new buildings. So that's something that's completely new, right? This is not a fitting with a bulb that comes as a separate part that we would have seen with fluorescence, with incandescence, with gas discharge. We have a fitting and a bulb are two separate things. This is a single fitting with the LEDs inside it. Why? Well, because the LEDs are going to last for such a long time. Like I said, 50,000 hours means that the LEDs are going to last as long as the fitting. So there's no need to have a replaceable lamp inside there. That is what I would expect to see as the technology continues to outstrip other traditional forms. So we should just see that the traditional way of constructing a light fitting is no longer valid. So you'll get something new and different. What surprises me is how complicated or how sophisticated the LED bulbs are getting that are designed to replace an incandescent one-for-one swap. So these are the bulbs that we're using in the workshop for our projects, right? So you can have a traditional incandescent fitting in your house. You don't need to change it. Just as that bulb blows, you take it out, put an LED bulb in, which I've done in basically every house that I've lived in the last 10 years. Yeah, as I say, what surprises me is how sophisticated those are becoming. And you'll notice the ones that we've got in the workshop, the glass bulb ones with the yellow filaments in them. And if you don't know what I'm talking about, ask me next time when we're in the workshop and I'll show you. What they've done there is rather than, let me think about this for a second, rather than change the way the bulb looks to suit the LEDs, they changed the construction of the LEDs to make them look more like an incandescent bulb. Easy to me, right? Because it doesn't make the bulb itself any better. All it does, and I know this sounds ridiculous, but it's 100% true. All it does is makes people who are used to incandescent bulbs more comfortable with upgrading to an LED, because they can see it just looks the same. It looks almost identical, so their brains go, oh, this is the same, I can use this. Which I think is the stupidest thing I've ever heard in my life, right? Seems crazy to me that you could have a technology that's superior in every way to the one that you're using, but you'll stick to the old way because you're used to it. So manufacturers have had to create LED bulbs that are so similar to an incandescent that you can't tell the difference in order to get people to use them. Why? I don't know. It's just ridiculous. Dumb. Dumb, dumb, dumb. Nevertheless, yeah, it's the boomers. Yeah. And like I can't emphasize enough that how real that is and how stupid it is. Yeah, if you can't picture what I'm talking about, hit me up next time we're in the workshop. But those glass bulbs with the yellow filaments in there, they are designed for one purpose only, and that is to look just like incandescent bulbs. There is no advantage to using LED bulbs that look like that, except that they are mimicking the incandescent. Yeah, and you're right, Jade. It's the same as internet banking or any other thing that we just accept as normal that for some reason people can't understand. And I don't know. It kind of makes me depressed about the world, right? That we actually have to change the way we do things to make people feel comfortable. Not because it's better, but just because people are stuck in their ways. They don't want to use something different. I mean, the day that I could buy LED bulbs off the shelf, I didn't give a shit what they looked like. The first ones I bought, that I installed in my house were corncob, what they call corncob bulbs. So it looks like a corn cob, but instead of corn kernels, they're little LEDs, right? And so this is, you had the corn cob with the bayonet fitting on it, and you just put that into your light socket. And it just looked like a bunch of LEDs, like a little corn cob looking thing, which, yeah, is undeniably weird. And okay, I can perhaps understand some people thinking that's a bit strange and maybe not wanting to use those. But on the other hand, like I said, they produce light. They're not a fucking decoration. It's purely it's a utility. So if I can get the same output from something that uses 10 times less power, I don't care what it looks like. But maybe that's just me. That's just that cold logic brain. Anyway. Okay, so we just got a picture here of, that's your typical GU10 and typical MR16. which we've talked about before. The bulbs themselves will look the same, but the different connections identify to us that this one here on the left is the GU10, which is the 230 volt, and on the right we have the MR16 12 volt. Again, as I said before, these days it's entirely appropriate to just pull out the old one, whatever that fitting is. You go and find an LED that looks the same and you can plug it straight in. It doesn't care about the transformer or anything like that. You just stick it in and it'll work. If any of you go and buy old style halogens or incandescents and I find out, I will I don't know, steal your lunch or something. It's ridiculous. Don't do it. And that's it. That's the end of that slideshow. Pretty quick, huh? No dramas. Questions on that one? Mm. Yeah, so it's a good point. It's a good point, Ray. Vehicle headlights. So again, if we look at the basics of the LED system, then they're no different from anything else. Dim LEDs exist and bright LEDs exist. There's nothing stopping you from having LED headlights that look exactly identical to traditional headlights. The problem that you're noticing is manufacturers that are making LEDs that are too damn bright. There's nothing stopping them from making them a little bit less bright. You may also notice that some of those will be xenon gas discharge, like a gas discharge lamp. We call them xenon headlights. So the old school incandescent headlights are pretty rare these days. So most of them will be a xenon gas discharge, and those ones are the really bright and white. But you also get LEDs as well. Yeah, it's nothing inherent about the LED system that that means those lights are too bright. They could make them a less white color. There's the whiteness or even blueness is part of what you're experiencing. I think it's a little bit irritating to our eye, or it appears a bit brighter than it is, but also the pure brightness. But that's just manufacturers. I don't know. I think it's just appealing to bogans, to be honest with you. They just put out the brightest headlights in the world, and people are like, cool, I want really bright headlights because they're dickheads. I don't know. It's a good question, though. Anything else from anyone else? Yeah. Yeah, protest outside. Hold it. Turn your damn lights down. All right. Okay, we'll cut it there, eh? We will let's break for lunch. I do have a phone call at 12, so let's come back at 12:30, eh? And we'll get the next one smashed out. Like I said, it should only take about an hour. So in the meantime, I've opened up the quizzes for discharge lighting and for LED lighting. So those are available to you now if you wish to try them out. If you do them now, then when we jump back on the call, you can ask me any questions if you've got any that you're not sure about, which will be helpful. But otherwise, you can obviously do those whenever you like, just like all the other ones. Do remember that I'm putting those due dates on them. All right, so we'll break there for now. Come back at 12:30. We'll do recess lighting, and that's us for the day. Everyone happy? We're good? Okay, I'll see you in an hour. All right, we're back. Have I got everybody? I have one. All right, one is enough. As long as I'm not talking to myself, I don't mind. Ah, two. There we go. Ray, and Jade. I can always rely on you guys. Excellent. Well. Tana's here and Rangi is here as well. Magnificent. Appreciate you all hanging around. Bailey's here. Cool. All right. Well, let's get straight into it. Let's get this one out of the way. I've got a couple of reports that I have to write this afternoon, so quicker we get it done, quicker I can do that. Are you guys seeing my slideshow? Does that come up? Perfect. Does anyone have